So good afternoon, everyone. It's me, Manjul Sitaula. This is assistant at FOSSEE. So welcome you all to the basic CFD workshop in OpenForm. So welcome you all to the basic level CFD workshop in using OpenForm. So this training is aimed to be a beginner level training session. It is aimed for the beginners, and these tutorials will be done in the foundation version of OpenForm, that is OpenForm version 9. So actually there are two versions, that is .org and .com version. So we are going with the foundation version. So if you have any queries, then please feel free to post a query in the chat as well as during the session. So the basic outline of this tutorial is that we will go through the basic process of CFD. This will be a brief overview, and then we will be simulating 2D laminar flow in a channel, and then we'll move on to the simulating the turbulent flow in the channel. So our problem definition. So we want to set up a case for the laminar flow through the channel first, then change our regime to the turbulent flow using K epsilon and K omega model. And then we want to post-process the results in ParaView. So I will just brief this the CFD process. So as Professor Nani has already described the in details about the process of CFD. So basically, the first process will include the domain modeling and physical modeling. So this means that we need to have a basic mind map of what we want to achieve or what physical phenomena that we are simulating and what are the possible outcomes that we want to achieve. So if our physical process depends only on the 2D or the 2D in 2 dimension, or the flow is changing in the 2D streamwise direction only, and there is no changes in the span-wise direction, so we can simplify our 3D domain into the 2D domain. So this comes under domain modeling, or else we can also use symmetry planes, like to if the flow is symmetrical, so we can use the symmetry plane. So uh, that also comes under domain modeling. So basically, before we start the simulation, we need to have the mind makeup of what we want to achieve. And the physical modeling is simply it means that how we want to represent our physical process in terms of mathematical equations and mathematical representations. So suppose if we have a heater or we want to simulate a case with heater, then we don't want like the physical component heater in our simulation. We can just replace that with the appropriate boundary conditions. That is, we can use the temperature boundary conditions instead of using the heater as a physical component. So this is the first process that we want to do before we dive into the simulation part. So after we are ready with this, that after we have a mind map of what we want to do and what we want to achieve, then we will move on to these next step, that is the domain discretization, which is also referred to as meshing or grid. We can call it the grid generation process. So it is the grids where we solve our equations. So basically, we have our equations in the PDE forms or differential equations form, but we cannot solve it directly in that form. We must make it convert it into the algebraic equations that I think you have already had a lecture on the first session. So the third process is the equations discretization. That is, we are converting the process of that we are converting the PDEs into algebraic equations, and we form the matrix system of a matrix with the global matrix, local matrix, and in order to solve that matrix and find our unknown variables, we need to find a solution method for that. So that comes from the solution method, like how we want to solve that matrix. So it may be like the Gauss seidel methods and so on. So moving on to the case structure, I think I don't need to explain much on the case structure. So we'll eventually get to these case structure and folders in a short while. So you can see a brief overview there with what files are included in which folders. So 0 and .ori contains initial and boundary condition files, whereas the constant contains the physical properties as transport properties. It contains solvent properties. It contains the mesh files after mesh is generated. So system is allows us to control our different parameters. So in system we have control dict, block mesh dict, every schemes, every solution. So in control dict we have the we can assign time steps, end time, output controls can be provided in the control dict. So we will eventually see this while we dive deeper into the simulation in the case setup. So as I've already said that before we run the simulation, we need to have a mind map and mind makeup like what we want to achieve. So first of all, we are doing it in a 2D. We are doing a 2D simulation. This is the first step. So we our 3D that the dimensions in the 3D direction or the in the Z direction do not affect our simulation. So this is basically the 2D simulation. And next is we are doing a laminar flow simulation first. So, so the laminar flow includes that we are doing the Reynolds number in that is less than the critical Reynolds number. So this Reynolds number should be in the laminar regime. So according to our Reynolds number, we will calculate our average velocity, that is our inlet velocity, and our kinematic viscosity is also provided. So you can see in this slide. So all the values, and we have calculated U average using the Reynolds number of 500. So L determines the characteristic length. So in our simulation, we have used height, that is 1 meter, as the characteristic length. So basically, there is also a concept of hydraulic diameter. So this is but when the width, that is the 65 meter is very large than the height, then we can just use the height as the characteristic length. Otherwise, we can also otherwise if it is more like a square shape, then we can use the concept of hydraulic diameter as well. So from the Reynolds number of 500, I've calculated U average. So you can also calculate this on your own using the calculator. So you will get a U average at 0.005, and then we will use these values in the boundary conditions. Okay. The next part is the domain discretization. So basically, before moving into how to discretize our domain, so I would like you to go to one of the site and download some files so that it will be easy for me to explain. So please visit the spoken tutorials website of FOSSEE. So basically you type spoken tutorials in your web browser first, spoken tutorials FOSSEE, and then you can go on to this second website, that is cfd.fossee.in. As you can see, not the first one. The first one is I think it is running slow. So let's go into the second one, spoken tutorials CFD FOSSEE. So click on that. So you will be directed to this page. So at the bottom, I think there is when you can see at the left side of the page, there is a green highlighted with the spoken tutorial. So please click on that spoken tutorial. So under the lab migration project, so there is written with a green highlighted. It is a spoken tutorial. So just click on that. So you will get directed to this page. So this is spoken tutorials page. So you can see that you can go. Here is the click here to access the open spoken tutorials. That is here in the second last link, I think, above the to install OpenFOAM 7. So there is one. Click here to access the OpenFOAM spoken tutorial. Just click there and wait for some time. So you are directed to the spoken tutorials, the tutorials for the OpenFOAM that is made by FOSSEE. So you can see here all the tutorials that are available to learn OpenFOAM. So I want you to go to the 9 tutorial, that is simulation of a 2D turbulent flow in a channel using OpenFOAM. So just click on that. So I think all of you are following me. If anybody is lagging, then please ask me to wait or repeat it. Okay. Now you will be directed to this page where you will also have a video of the tutorial case. So you can always look at it after the in your free time or after this workshop also. There are many other tutorial cases also available in this website. So scroll down, and at the right hand side you can see that there is a code file name. There is a interface in where there is code files and there are files available. So just click on that code files. So after you click on code files, you can see that the code files are downloaded. So it must be located in in your download folder. So just unzip this So extract this. So after extracting, now you can see that we have a zero constant and system folder inside that. So this is the basic structure of OpenFOAM. So I think you have downloaded this, and you can, after downloading, you can access it inside that. So you can see that there are zero constant and system folders inside those in these files. So what I want you to do is just go to system and the block mesh file, because we need to first make the mesh, then proceed to the simulation part. So first we'll look at the block mesh, how to generate mesh. So just open your block mesh file. Okay. Okay, now I'll show you my slide along with this. So actually, in this downloaded one, there is no mention of 0, 1 to vertex, but for the ease of understanding to the users, I have created a separate file, but the coordinates, all the files are same. But just for you to understand, I have commented out some things. So let me, the file is same. So what I want to say is that these and these files are same, but what I have included is I have commented some vertex number in this, so that it will be easy for you to understand. So this is not actually required. This is a comment. This will not be executed because we have commented it. So this is for you to understand. So now let's look at this slide and this. Okay. So first of all, before doing that, let me help you visualize how is our flow and from which direction is the flow moving, what is our flow direction. So we can see that in this 3D domain that we have an inlet face here shown by this cursor and outlet face at these faces. So they are all together: inlet face, outlet face, the back face, at the back of these 3D domain, and these block 1 and block 2 as the front face. So we have also have the top face and the bottom face, but I have not written here the names, but there is also a top face and the bottom face. So we can see that the flow is coming from this direction where there is inlet, and the flow, and and in this face there is outlet. So we have already learned to make the domain using a single block, but now we are making a block 2 over block 1. So basically to make a single block, so let's first look how to make a single block. So in order to make a rectangular block, how many coordinates do we need? Actually, we need 1, 2, 3. That is this coordinate, this coordinate, this one. That is the 4 coordinate in the front face and the 4 coordinates in the back face. So actually in the front face we have 0, 1, 2, 3. So I have named this 0, this coordinate as 0, this coordinate as 1, this coordinate as 2, and this coordinate as 3. After I have named in the front face using this 0, 1, 2, 3, now I also need to assign the coordinate that is the x, y, z of these coordinates. So actually this is just naming of the coordinate 0. This I refer to this as 0 coordinate. I refer to this as 1 coordinate. I refer to this as 0 coordinate, but they have their own x, y, and z points. So in order to make this block 1, we need actually 8 coordinates. That is the front 4 coordinates, and there is also a back face at the back which requires 4 coordinates. And after we join this front and back face, then we will be able to create a block. That is, we will be able to create block 1. Similarly, for block 2, we need this coordinate, this one, and this one in the front face, as well as in the back face. We need 4 coordinates. So at this I have written 0, 6. So this referred to as 0 is at the front face and 6 is at the back face. So I think you are getting this. And this 1 is at the front face and 7 is at the back face. And this 2 is at the front face and 8 is at the back face. But we can see that the between 4 coordinates are shared by 2 blocks. So we can see that we can use the same coordinates 2, 8 and 3, 9 to make 2 blocks. That is because these coordinates are being shared between these blocks. So in this way, we can make block 1 and block 2. Now let's move on to our block mesh file. So you can see that now So you can see that the zero coordinate that is I have named as 0, that is the origin 0 comma 0 comma 0. Now the one the I have named it as one coordinate, that is this coordinate, which is in the front plane, that is 0 plane. So this 0 represents z direction. Now in the back plane, that is in the z direction of 0.1. I think you can visualize this. So this 0.1 is at the z axis and at a distance 0.1, the back plane. So the first coordinate is 0 comma 0 comma 0, right? The first that the one number coordinate would be 65, that is x-axis it is in 65, and y-axis it is still 0, and it is at the front plane. So the z direction will also be, the z coordinates will also be 0. But now we move on to the 2 number coordinate, that is this coordinate, 2 number coordinate in the front plane. Actually 8 number coordinate is in the back plane, that is in the z 0.1 distance. But 2 is in the front plane. So 2, we can see that how can we give the coordinates for 2? That is, we can provide it as x-axis it is still at 0, but in y-axis it has moved some distance of 0.5. So actually we have a total distance of 1 in the y-axis, but after doing it half, we have 0.5 and 0.5. So the coordinate of 2 would be 0, that is x-axis is in 0, and y would be 0.5, and z is 0, that is it is in the front plane, that is the number 2 coordinate. Similarly, number 3 coordinate would be this, that is x-axis 65, y-axis 0.5, but and it is in the front plane, that is at 0. So similarly, after we complete the front plane 0 1 2 3 4 5, now we move on to the back plane coordinates, that is number 6 coordinate. So 6 number coordinates, you can see there here that we are moving now z to 0.1, that is we are doing for the back plane. So it would be the same as 0 1 2 3 4 5, but we will just keep z as 0.1. So actually these are the same coordinates but in the back plane. So just we can change the coordinates of z to incorporate this effect without changing the other x and y coordinates. So I think you understood this, how these coordinates are formed and how blocks are created. So we can, to create block 1, we need 0 6 1 7 2 8 and 3 9 coordinates, that is 6 coordinates. Similarly, to create block 2, we need 2 8 3 9 4 10 and 5 11 coordinates. Actually this 5 11, this is for nomenclature, just to for the users to understand. You don't have to do and comment down 0 1 2 3, but it would be easy if you, for the beginners, if you can do this way. Okay, now we need to create a block. We have assigned our coordinate. Our coordinates are ready, of all the vertices are ready. That is, to make a block we need vertices. So our vertices are ready with the prescribed coordinates. Now we need to use these coordinates to create this block. So now I want to create block 1. So what is block 1? So using these coordinates. So at the front plane we have 0 1 2 0 1 3 2. Actually, to make the blocks, the convention is you move in the anti-clockwise direction or you move in the clockwise direction. That does not matter, but you have to follow the same convention in both the blocks. Okay, you can now see that to create block 1, we need the coordinate of 0 1 3 2. That is, first we will include the front face, that is the front plane coordinates, and then we will include the back face coordinate, that is 6 7 9 and 8. But we can see that 0 1 3 2, that in that convention only we need to assign the back plane coordinates also, 6 7 9 8. We cannot do 6 7 8 and 9 because we have done 0 1 3 2, right? If we had done 0 1 2 3, that is 0 1 2 3, then we should have done 6 7 8 and 9, that is 6 7 8 9. But we need to follow the same convention while creating the blocks. Similarly for okay, I have created the first block, that is 0 1 3 2 and 6 7 9 8. Now this, after that, this after you assign the coordinates to the block, now you have to assign how many grids you want to generate on that block. So this is the x-axis grid, this is the y-axis grid, and this is the z-axis grid. So I have already said that we are doing a 2D simulation, and that was our first step that we have already processed. So we don't want to simulate in the z direction. That is, the z direction won't affect our flows, that won't affect our results. So we can just assign any value of z coordinates. So I have assigned here 0.1. You can assign it as 0.2, 0.3, 1, 2, that won't affect our 2D simulation. And you can assign any coordinate number here, 1, 2, 3, 4. That won't affect our simulation, because we are only trying to do a 2D simulation, not a 3D simulation. Okay, I think you understood how to make a block, and these are the number of grids in the, that is, I need to make 75 grids in the X direction. I need to make 30 grids, or you can 30 boxes in the Y direction, and a single grid in the Z direction. Okay, so after that I am doing a simple grading. So simple grading means that, so for the laminar case, okay, for the laminar case, I think you have already now I don't need to show the slide that we have made the blocks out. You know how to make the blocks. So let's move on to the grading. So grading actually means like biasing in ANSYS. We have bias factors in ANSYS. So if you want to if you want to capture the gradients at the boundary layer effectively, then you need a very fine mesh at the boundary, and you can have a coarse mesh near the center of the flow. So if it is a rectangular, we have a rectangular channel, so we have to make a very fine mesh to capture the velocity gradients or the gradient values in the near the walls. We can have a coarse mesh at the center. So this simple grading will help to control these size of meshes near the walls or at the center. So basically, for the now at the first case, what we want to do is we just want to do a laminar simulation with just simple grading of 1 1 1. So this means that our grid size is uniform along all these blocks. That is, it won't one all the sizes of the mesh will be similar. So if the mesh is if one of the mesh is like 0.1 meter, then another mesh in the X direction would also be 0.1 meter. So this is a uniform grading. If you provide 1 1 1 or 1 1 and 1 1 1. So I will stick with this for now. I want to do a laminar case now, and I will change it, and I'll show you how to change these values also, so to make a growth layer or to make a biasing in the Y direction, which we will do for the turbulent cases. And we should also do for the laminar case, because we want to capture the velocity gradient, and there is a boundary layer formation in the laminar case as well. But for the basic understanding, I am just sticking to the uniform simple grading now. Okay, now after we make the blocks, we have made block 1, and this is for block 2. So we have completed to make our block. So edges, we don't have any arcs in our domain. So you can see that from the block mesh stick, we can create the CAD model, as well as we can mesh it inside this block mesh stick. So we don't want any CAD model from outside or third-party software. We have just created a model, that is a 2D CAD model, and now we have also made a mesh for this. So using this number of cells. So this is what block mesh can do. So you can make a mesh without having to import any CAD models, like in third-party software, where you have to make a CAD model first, then export it in the import it in the different software and such things which have to be done. But here we are creating the domain and meshing it inside the block mesh all together. So the edges are not required. Now for the boundary, so you can see that we have created the boundary names at lower wall, upper wall, inlet, outlet, and front and back. So you can see at this presentation that there are altogether 6 faces. That is the inlet, outlet. So it is inlet, outlet, and we have front and back. That is we have written block 1 and block 2. It is the front face, and this is the back face, and this is the upper wall, and the below is the lower wall. So now if you there is also a convention for writing these boundaries. Okay, now we have named our boundaries as these lower wall, upper wall, and we can see that the walls are of type wall, whereas the inlet and outlet are of type patch. So whatever is not a wall is a patch. So if there is no wall, then you need to keep it as type patch. So inlet and outlet, we have assigned patch, and for the walls we have assigned the wall boundary condition, and for front and back we have assigned empty, because this is our 2D simulation. we are not interested in the span-wise effect. So we are also stream-wise. We are only considering the stream-wise direction. So we have just kept front and back as empty. Now, how do you name this using these coordinates? So actually, all this we need to you do it using the coordinate that we have used here, the number of coordinates. So we have really start from zero. This is zero coordinate. This is one coordinate. This is two coordinate. And using this coordinate, we need to create block. And using this coordinate, we need to assign the faces as well. So you can see that. Okay, let me teach first from the inlet face, because it will from the inlet face it will be easy. So you can see that actually inlet face is this face, right? This is, but this is in a 2D, so you need to visualize. In these, there is also a face in the span y direction, in the span direction. So using this 0, 6, 2, 8, and 4 and 10, using the six coordinates 0, 6, 2, 8, 4, 10, we need to define our inlet face. So you can see that we have defined 0, 6, 8, 2, 2, 8, 10. For using these four coordinates only, we have declared our, or we have made our inlet face. But there is a convention for that. So what we have done is 0, 6, 8, 2. So 0 is in the front plane, 6 is in the back plane, 2 is in the front plane, 8 is in the back plane. So what we can do is you can use a right hand rule. So, and you can point your thumb either outside or either inside. So if you point your thumb outside, then you need to follow this convention throughout when you assign the faces. And if you point your thumb inside, then you need to use this convention while doing for the other boundaries as well. So here you can see that 0, 6, 8, 2. We are doing it. We are pointing our thumb inside while doing this convention. So 0 is in the front plane, 6 is in the back plane, 8 is also in the back plane, and 2 is in the front plane. So if you using right hand rule, if you call your fingers in this direction 0, 6, 8, 2, then you can see that your thumb will be pointing inwards of these inwards of these edges or of these faces.
Yeah.
So you can see that we have like we know how to create a mesh or to disguise our domain using these coordinates and all this. So now I'll not dive deeper into these, how to do these conventions and nomenclatures. So after our block mesh is ready, now we are ready to generate mesh. Now we'll start setting up our case. Now I would like all of you to open your terminal. So basically you can just open Ubuntu. So I think all of you have opened Ubuntu. Now I will type one command. This is because I have different versions of OpenFOAM installed, and I have LAS, the OpenFOAM 9 version with OP9. So I am typing this. But if you have only a single version installed, you don't need this command. Okay. After this, now follow me with these steps. So type run. So you can see that after typing run, you will be redirected to the run directory. And if you type ls, then you can see that this in my run directory, I have multiple folders, but in your run directory, there is only, I think, cavity case. So let's create one more directory in this run folder. So let's create a directory called Laminar. So type this command mkdir laminar. So we are creating a new folder in the run folder. So now if you do ls, then you can see that a new folder called Laminar is created. So you can, I think it is also visible in your terminal. Now we want to copy our test case to this Laminar so that we can edit that template. So let's use the previous case as our template case. So what I would like you to do is, I would like you all to type this command to copy from the cavity case to the Laminar case. So before doing this, you can also get inside to the Laminar folder. So just type cd Laminar. So now you are inside the Laminar folder that you have just created. Now we want to copy from cavity case to our Laminar folder, right? So we need to type cpr. So where is our Laminar? Where is our cavity case? It is inside the cavity case. So just copy this address, location path, then right click, it will paste in the terminal. Right click will paste this. Now we want cavity case, right? So just type CAVITY cavity case. Inside the cavity case, there is another folder called cavity inside your cavity case. Okay, now we want the zero system constant that is inside the cavity to be copied in our laminar folder which we have created. So to do this, just put a asterisk and put a space and then dot. This will copy the folders that is inside the cavity folder, which is inside cavity case, in the laminar folder. So if you do this, so all of you follow this first. So basically I've copied this location here and then use an asterisk. So why I use asterisk is because I want to copy, there are different folders inside cavity, right? Zero, constant and system. There are 3 folders. So I want to copy that 3 folders in my laminar folder which I have created, and we want to run the simulation on this folder. So after this, press enter. So after this, if you press enter and then you do ls, you can see that you have copied the zero, constant and system from the case that you have run. But I think there are other folders inside the cavity because you have already run the simulation, right? So what you can do is, before copying, you can do home clean case. After copying, you can do home clean case or home clean tutorials if that works, and it will delete all the other folders. So type this command. Because I have not run the cavity case, so I have only zero, constant and system folder inside the cavity. But if you have run the case, then there will be additional time folders. So we don't want that for now. So after you copy, just run form clean tutorials and see if that will clean everything except zero, constant and system, and let me know. And do ls. So if that cleans or not, one of you can just reply me. I think everyone is following me on this. So if I'm a bit faster, then please let me know. Okay, you can ask your questions by unmuting yourself.
I tried up to cp -r, and it says that it cannot. No such files on the directory. Followed every command. That's cp9. Yeah, that one.
CP.
Yeah.
So actually, what you can do is CPR and then the location of your folder, that is the cavity folder. So in my, it is located in OpenFOAM Manjil 9. This is the username. Run, and inside that run, there is cavity case, and inside the
Do I
cavity
have
case, that is
to put the dot?
cavity.
No, I don't. Okay.
You,
I
you
think
should not include Manjil 9. It should be your own location.
yeah, I got that. Thank you.
So anybody have any problem in this, or have you followed up till now? One of you can, if you have problem, you are facing problem, you can unmute yourself and ask me. So I think everybody inside the laminar folder, you have zero, constant and system folder. So now you can also see this by going in from the file explorer section. So if you go inside Ubuntu, inside your home, inside this, and so let me make this. Okay. So inside this, if you go to OpenFOAM, and you have your own folder that is created, and inside your own folder you have your laminar case that we have just created, and inside the laminar case you will have zero, constant and system folder. So everyone is followed till now. Please raise your hand and ask questions if you have not.
I typed the same as you said, but inside Laminar flow, our home, this folder is empty. It is showing.
It is empty.
Yeah.
So did you run this command cpr cavity to?
I did, but
So okay, I will.
this shows that no such file directory.
Manzil,
Yes.
you can show them how to copy it manually only. since they must have saved it in different locations. Some of them must have kept it in their downloads or not. So you can just show them how to manually copy and paste it in the file explorer itself.
Okay.
Actually, when I did ls, mine shows 0, 0.1, 0.2, but yours shows only 0, constant, and system. So
Okay. Did you run form clean tutorials?
no, I didn't.
Try this and see. Try this command first.
Is it possible
Yes,
for
yes.
you to show again how to create the Hagen Poisson parabolic one in the run folder?
No.
And
We are not dealing with the again Poichoy flow. We are just this I have kept in here because I had run the simulation all
those
earlier.
are already run, right?
These are not. This will not be in your run folder.
Yes.
You
So
will only
now,
have the cases that.
so in run, I will write CD laminar, right?
Yeah, no. Okay. Let me start from the first. So just type run at first. So this will direct you to your run folder, right? Okay. After that, just type ls. Now, if you type ls, then you can see that I have multiple other folders because I have run many simulations in this inside this run folder. But in your case, there should only be cavity case, right? So that is inside when you go inside the run folder, that is in Ubuntu home and then open form. Inside this run folder, there will only be cavity case. So if you type this command,
Yeah, I can see like I have here cavity case and PIDS daily. That was yesterday.
okay,
That
that
was
was
the model. Okay.
yeah. That will be that two folders will be there,
Yeah.
but apart from that, there will be no additional folders. So what I want you to do is just create one folder called Laminar by running this command. So press enter. Now we will what we are doing is we are creating a Laminar folder. But I have already created a folder called Laminar, so it said that cannot create directory. If you have not created, then just type mkdir Laminar.
I'm sorry to interrupt, but could you please explain what that command form clean tutorials do exactly?
So after you ran the complaint tutorials, did all of the time step vanish or not?
Okay, it clears the time step data, right?
Yeah. So actually, what it does is it will revert it back to the original configuration that was previously. So it would clean all the files. It is like cleaning the folder and only keeping the original folders in this folder in the system. So the simulation that you have run, it will clear all those time steps and all those simulation data by this command.
Okay, understood. Thank you.
So I think you have all created a folder called Laminar.
Understood. Thank you.
Okay, fine. So you have created a folder called Laminar. So if you do ls, then there should be like a folder that is called Laminar being generated.
Hello, Manjil.
Yes.
John here. So I think on the terminal, because your username is different, their username is different, people are making mistakes. So can you show them by the GUI version only, like from the folder only, create and just copy? That will be much simpler, I guess. Or
Okay.
are some of them? Yeah. Here only you show them, because what is happening is otherwise everybody has different username and they don't know what they are doing. So here it will be much quicker.
Okay,
Yeah.
sir. Okay, so what now apart from the terminal, you can do it manually as well, like copying the folders. So in your run folder, you must have cavity case, right? And you have also created a folder called Laminar. So in your run directory, there must be this cavity case, and then there must be a folder called Laminar. And if in another folder, it might be piece daily, which you have created yesterday. So what I want to do is copy this zero constant and system, only the zero constant and system, not the other time directories, just the original folder, that is zero constant and system. Just copy, and then after you have created a folder called Laminar, then you just paste it here. But by doing this, you can see that some additional files are being generated. So you can just delete this, because this but when you do it manually, this kind of files get generated.
Just a quick question, like I wanted to know, like should I the copy the zero constant system from the cavity case or cavity, or does it make any difference?
No, we are just using as a template case, so you can just copy from cavity only the zero constant system inside the cavity case.
Okay.
So have you all done up to this? Like you have copied?
Yeah.
So you can. Okay.
I
So I
mean,
think
if time allows, could you please show me how I can do that using the terminal? I mean, copy the zero and the other folders.
Manzil, for if you want to complete the tutorial, it will just keep delaying. So see, there are simple commands you can do that. You can search online. Let Manzil finish, otherwise he will not be able to demonstrate. He has to demonstrate a laminar case as well as a turbulent case.
so you can see these afterwards. So you can see that by manually copying, we can see that an additional folders will be created. So you can just delete them. Now we have in the zero we have P and U, and in the constant we have transfer properties, and in the system we have our block message control every skin and every solution.